I would like to do my own chairman. And this is the first day of the workshop, almost 4-week workshop. And the idea of this workshop is just, get together. And as you have already noticed that our schedule is not very tight. Except for Mondays, we have only 2 talks, one in the morning and one in the afternoon. So the idea is discussion among participants, casual discussion, not the formal discussion only in this place, but there are many open rooms available for free discussions. So I would like to suggest that you guys to communicate with each other. Okay, so since this is the first talk, I would like to talk a little bit about everything, basically, more or less. And I'm going to touch upon every subject, even, a very superficial way, only on the surface. And please ask deep questions of the speakers of every subject, which I indicate in the slide. Okay, first of all, I would like to show this, slide, thanking our sponsors. The biggest sponsor is, of course, the Institute for Solid-State Physics, University of Tokyo. And this is another source of our money. This is Ministry of Education project, Challenge of Basic Science. This is most of the travel money for the participants is from this budget. And some of the financial support is coming from this another project of Ministry of Education, which is entitled as Creation of New Functional Devices and High Performance Material to Support Next Generation Industries. Anyway, these 2 projects are related to the K Computer, which is located in Kobe. And we are now struggling to get another funding for next one. Anyway, the last one is called the PCOMS, which is also related to Ministry of Education, but this is not completely directly related to the K Computer. This is for a program for training researchers for the next generation. Anyway, we have these sponsors. Okay, let's start the scientific subjects. Okay, there are, I'm going to talk mainly about the tensor networks in this introductory talk. But the tensor network is not the only method for dealing with quantum many-body systems. And before getting into the subject related to tensor network, I would like to mention several numerical methods, which are quite powerful depending upon the nature of the program. Okay, I would like to start with good old quantum Monte Carlo. And the quantum Monte Carlo is basically the Markov chain working on the path integral configuration space. And basically for given Hamiltonian H, suppose we want to compute expectation value of some quantity Q. And then what you would do is first you expand, you represent the partition function in terms of in the language of the path integral, Feynman path integral. In this particular figure, I used discretized imaginary time, but this is just a conceptual. And in the end, you can work directly with the continuous imaginary time in a program, and which we usually do. But anyway, this is path integral, Feynman path integral, and this line representing either up spins in the case of quantum spins, or the particles in the case of particle physics. in any way, in either case, you deal with this kind of patterns. This is real space direction, and the axis corresponds to the imaginary time direction. And the expectation value of whatever Q you would like to compute can be computed by this equation. And basically, quantum Monte Carlo is classical Monte Carlo in the space of worldline configurations, because worldline configuration is classical degrees of freedom, basically. So you can do many things with this quantum Monte Carlo. And this is just one example, and I picked up this example because we have been involved in this subject for many years, and also tomorrow, probably Professor Anders Sandvik is going to talk at least something about this, I suppose. Anyway, this is a transition between magnetic phase and non-magnetic phase, and it is also called the deconfined critical phenomena. Because on one side of the phase, for example, in this particular case of SUN-JQ model, it is known that on one side we have on one side we have a null state in which the SUN symmetry is broken, and on the other side of the phase, or the phase transition point, we have this kind of phase in which each pair of spins, nearest neighbor spins, form singlet pairs, and and as a result, the lattice rotational symmetry is spontaneously broken, but SU2, in this case, SU2 symmetry is not broken. So the reason why we call it the deconfined critical phenomena is as you approach the critical point from this side, as you approach the quantum critical point, the binding potential, binding force between neighboring spins becomes weaker and weaker, and as you reach this point, then these spin-ons are dissociated. So exactly at this point, you have a free spin-on gas. And I think, if I remember correctly, Anders Sandvik did some calculation based upon this free spin-on picture, and they obtained a very nice result about low temperature specific heat and other things as well. Anyway, this kind of deconfined critical phenomena was first proposed. The detailed scenario, field theoretical scenario, was proposed by these guys in 2004, and they discussed this new type of phase transition. And one peculiar aspect of this phase transition is it is not really the simple spontaneous symmetry breaking, because you cannot say which side of the phase has a higher symmetry in this particular case. So in 2007, we did not really, in this particular work, we did not directly study this quantum phase transition, but we just studied the SUN model without this term. But even for this pure Heisenberg model, SUN Heisenberg model, we observed the circular distribution of the order parameter, which means that at this point, this model itself is on this side actually, but still even without this term, the system is close to the critical point, and as a result, what you observe is a kind of circular distribution of the order parameter. And on the same year, Anders Sandvik first obtained a direct numerical study of this particular quantum critical point, and they demonstrated that indeed the rotational symmetry is broken on this side. However, the rotational symmetry is recover exactly at the quantum critical point. I'm coming back to this point in the next slide. Okay. In any way, as I said, this is described by a pair of spin-ons on this side, and these pair of spin-ons are unbound as we approach the quantum critical point. That's the confined critical phenomena. And we did somewhat large calculation using the K computer and also ISSP supercomputer sitting over there on this same floor. And what was disturbing was, okay, this is, by the way, this is the scaling dimensions of all the parameter. And I think this is the scaling dimension of the magnetization, and this is the scaling dimension. Oh, okay, this is the 1 over nu, and this is 2x. 2x means scaling dimension of the magnetization and the dimerization of the parameter. And what was disturbing was, okay, horizontal axis is the system size. So this is the system size dependence of the effective critical exponent. And what we observed was, I mean, as you can clearly see here, as you go to larger and larger system size, the effective critical exponent becomes very larger and larger in the case of 1 over nu, and it becomes smaller and smaller in the case of 2x, the scaling dimension of the magnetization. And I don't remember which was which. I think here we have two sets of estimates. One is for the magnetization, and the other is for the dimerization of the parameter. So anyway, this was somewhat disturbing. So it was the system size restricted finite size scaling. The result of this is depicted here. And as you see here, it has a strong size dependence, and scaling dimension systematically shifts to some, I mean, in the case of 1 over nu, it's systematically increased. And quite recently, I believe Anders is going to talk also about this at some point of this workshop. And in any way, quite recently they did the numerical renormalization group calculation for classical 3D XI model. Because so up to this point, I mean, I have been talking about the quantum SUN model and quantum JQ model, and everything is quantum lattice system. But this strong size dependence suggests that we have to think more carefully about the renormalization group flow. And even in the original work by Penfield and workers, they pointed out that there is a there is a dangerously irrelevant scaling field at the deconfined criticality. And this dangerously irrelevant field is related to the lattice rotation symmetry breaking field, which naturally arises from the fact that we work with the lattice system, which doesn't have the rotational symmetry from the beginning. So we have to take into account such effect of rotational symmetry breaking field. And this is what they aimed at. So it may be a good idea to think about the classical counterpart in order to get more accurate result compared to the quantum counterpart. So as I said, one of the causes of difficulty of the quantum case may be the presence of the dangerously irrelevant field. That's why they did this, I believe. And so this is basically the Monte Carlo calculation of the renormalization group flow diagram, in which vertical axis represents the symmetry breaking field, and horizontal axis is basically the control parameter which corresponds to the coupling constant. But actually this is actually the Binder ratio, but Binder ratio can be regarded as a dimensionless coupling constant, basically. So that's what they did. And don't ask me deep questions about this result. Please ask Anders about this work. So, okay, this is very interesting development. That's why I wanted to mention this at the beginning of the workshop. And however, there is a big problem, which is very well known also, that probably most of you already know this technical problem. This is a technical problem, but this is inherent technical problem, so it is kind of important technical problem. So it is called a negative sign problem. And for those of you who are not familiar with Monte Carlo simulation, let me, in any way, let me explain what is the problem. So in quantum Monte Carlo simulation, as I said, basically partition function is expressed as the summation of some weight factor, some weight, maybe the Boltzmann weight, something analogous to the Boltzmann weight, which is represented by rho of pi here. And summation is taken over all the configurations of Feynman path patterns. And this pi represents the, for example, in this picture, this whole configuration, whole pattern of the warp lines. And as long as this weight is always positive, then we can interpret this as a weight, and we can carry out some metropolis algorithm by defining this as a probability. This pi prime is the final configuration, and pi is the initial configuration, and whenever you try to move from pi to pi prime, you accept such a movement by this probability. That's the metropolis algorithm. So as long as rho pi is always positive, it is easy to construct a quantum, Monte Carlo simulation or Markov process based on such a weight. However, if, for example, we have three spins antiferromagnetically coupled with each other, then there is a problem. And no matter, this, for example, you can easily realize that because this is a warp line of particle or up spins, and if particles follow this trajectory, and then every time the particles hop from one side to the nearest neighbor side, then you get a negative factor minus j if the spins are antiferromagnetically coupled. And if we have three sides, a triangle of spins which are antiferromagnetically coupled, then in principle, with some probability, you have this kind of configuration, which gives you minus sign, which means that this weight factor can be negative. And as I said, so in such a case, you cannot interpret this as a probability, so you have a problem. This is negative sign problem. So, okay, this is what we have already discussed. So, as long as this problem doesn't exist, for example, in the case of SUN JQ model, which I discussed in the last slide, you can do the quantum Monte Carlo simulation without negative sign problem. And there are many interesting systems you can simulate without negative sign problem, but on the other hand, there are also many problems which causes negative sign problem. So for such systems, in particular, a typical example is frustrated quantum spin systems or fermion systems. In those cases, you might want to develop other methods. So this is one of the methods you can use in such cases in the model, for the model with negative sign problem. And for this, probably Professor Imada and Dr. Misawa, I don't know whether they really talk about this. I didn't ask what they are going to talk about, but this is just my guess. I guess Professor Imada and Dr. Misawa are going to talk at least a little bit about this, or maybe much about this. Anyway, the method is basically a variational method together with some Monte Carlo estimation. And here, the variational wave function is this psi, and this variational wave function can be expressed the initial state, which is basically the Hartley-Fock-Bogoliubov type wave function. Formally, it is defined in this way using this factor Fij sigma prime, and I and j represent sites, and sigma and sigma prime represent spins. And basically, this is Slater determinant type wave function, and to this Slater determinant type wave function, you apply a quantum number projector, which is represented by L here, and also the other factor, Witts-Willer or Jastrow factor, which is represented by P here, in order to take into account the correlation effects. And okay, there are many literatures. I only picked up only 3 or 4 of them. And in any way, the important thing here is you can do calculation without negative sign problem by using this kind of technique. But however, instead of sample all the configurations by the Monte Carlo simulation, you have to compute the Pfaffian of some matrix X, which is linearly dependent on this term, on this factor. So for computing the Pfaffian, you have to expect a larger amount of computation is necessary. So this is basically variation of Monte Carlo. And okay, yeah, this is, I just talked about quantum Monte Carlo and variation of Monte Carlo, but there are many other interesting methods which is going to be discussed during the workshop, I think. Okay, let's move on to tensor network. And tensor network can be regarded also as a variational wave function. So this is a tensor network variational wave function, and expanded in terms of some orthonormal complete basis, which is specified by n spin variables, let's say. In the case of quantum spin systems, the most common choice is the simultaneous eigenstates of all z components of all spins, as usual. So this S through Sn is just the eigenvalues of z component of spins. And then if you expand, you can actually, in general, you can expand any quantum wave function with respect to such a orthonormal complete basis. As long as this part is general coefficient, then you can express any quantum states. But here I propose to express this coefficient in terms of tensor network. That's the tensor network wave function. Okay, to be more specific, the coefficient here can be represented by this kind of diagram. And the meaning of this diagram is, in this case, you consider 8 tensors, and each circle represents tensor. For example, this T8 represents rank 3 tensor because it has 3 legs, and 3 legs corresponds to 3 indices. So basically, T8 has 3 indices, 1, 2, 3, and T7 has 4 legs, which means that the T7 is a rank 4 tensor. And these blue lines connecting to tensors are indices which are to be summed over. In other words, for example, this index appears twice, basically. Appears once as an index of T7 and once as an index of T8. So it means that this particular blue line appears twice. This index appearing twice should be taken as a summation index. That's basically Einstein rule, Einstein convention. So here, the network itself corresponds to the Einstein convention, basically. And also here we have open ends, and open ends are connected to these variables. So once you fix these variables, all the z components of the spin variables, if you fix them to some values, then you get one number represented by this whole diagram. That's the coefficient you have here. So the advantage, what is the advantage of this type of coefficient? So in general, if there is no structure in the coefficient here, if there is no structure, then how many coefficients do we have? Since we have n variables, suppose this is 1-bit variable each, then there are 2 to the n's combinations here. So it means that if we don't assume any particular structure of the coefficient, we have 2 to the n independent variational parameters. And as you can imagine, such an exponentially large number of variational parameters is not manageable as you reach moderately large system size. Maybe 10, n of 10 may be okay, but n of 20 and 30, the things becomes complicated, out of hand quickly. So instead of working with non-structured coefficient, by working with this kind of tensor network type coefficient, you can reduce the number of independent variational parameters by a great deal. For example, in this case, this is just a schematic picture, so we cannot tell much from this picture, but in typical application, which we are going to see later, in typical application, the number of tensors is basically proportional to the number of sites. So in this case, we have 8 tensors, but in typical application of tensor network state, we have, if we have 100 spins, then the number of tensor is also, of the order of 100. And in most cases, on top of that, in most cases, we can assume the translational symmetry. So it means that every tensor has the same elements, which reduces even further the number of independent variational parameters. So, this is just the idea of the tensor network ansatz for quantum state. Okay, this is the simplest variational tensor network. The simplest tensor network is, of course, the direct product state, in which the tensor is connected only to its only to one physical index, physical variable, and all the tensors are not connected with each other. So if you use, of course everybody knows the answer, right? If you use this type of tensor network, direct product state, and apply the variational principle, then optimize the wave function. Then what you get is basically a mean field type approximation. So you always, this kind of tensor network state end up always with the mean field type approximation. So in principle, maybe even this might be useful in some cases to get a quick answer to some problem. but usually you might want to have better approximation. And so something more complicated than this, but still manageable. That's another important factor. I mean, the resulting network must be manageable somehow. So more complicated but still manageable network is going to be desirable. And this is the second example I would like to mention, which is known for many years under the name of DMRG, a density matrix renormalization group. And actually, in retrospect, maybe not really in retrospect, I mean, people are aware from the beginning, but anyway, this DMRG method can be viewed as the variational wave function with the second simplest tensor network. Here, the second simplest network means that matrix product state in which the tensor network, so the simplest example was something like this, right? And the second simplest one is the chain. This is the second simplest. And this second simplest tensor network already gives a very accurate description of the 1D quantum systems. That's what we learned from the, many interesting developments related to the DMRG. Okay, in any way, if probably most of you know what the DMRG is, but in any way, let me go through quickly the procedure of DMRG. So you start from some initialization. This doesn't have to be zero, but zero is just the simplest starting point. こっちじゃないとね、電池は一応持ってきてるんですけど。Okay, starting from some initial configuration, some initial point for the Hamiltonian and also the local operator. It can be anything basically. In principle, it can be anything. Then you consider the Hamiltonian of subsystem. Oh, this is already a Hamiltonian subsystem. Maybe I should draw some picture of this. What I'm talking about is something like this. Here is some subsystem A, and here is another subsystem B, and we are going to insert additional spins A, 1, 2, B, and we are going to call this part A tilde, and we are going to call this part B tilde. That's the notation you are seeing here. Can you see the picture? Actually, I cannot see the picture. Okay, this is better. This is A tilde. This is B tilde. Okay, this is better. Okay, then the idea is you want to have the Hamiltonian, effective Hamiltonian that describes the subsystem A and subsystem B, and also you repeatedly you insert these two spins. Repeatedly. And in the end, you expect that this whole procedure converges to something. And that hopefully that represents the infinitely large system. That's the basic idea. And Hamiltonian HA tilde is the, maybe I should have written H of H sub A tilde instead of H tilde of A. But anyway, this thick line represents the subsystem, original subsystem A, and this thin line is corresponding to additional site 1. And this H tilde represents the Hamiltonian for this combination of original subsystem A and the newly added site 1. That's the meaning of HA. So HA tilde is naturally the summation of two things, which the first one is the original A part, original A Hamiltonian with just a straight line. And the additional part is, of course, the interaction between original subsystem A and the newly added site 1, which is represented by this in the case of antiferromagnetic Heisenberg model. And if the Hamiltonian is different, you have to change this part a little bit. But the idea is the same. And yeah, you know, I mean, this is sigma A alpha means that the boundary spin, the spin on the edge of A. And this sigma 1 is, of course, the spin, quantum spin located at site 1. And this is this term is describing the Heisenberg interaction between the spin 1 and the edge spin of subsystem A. And then the Hamiltonian of the whole system is, of course, the summation of HA tilde and HB tilde and the interaction between two central sites, 1 and 2. So that's the Hamiltonian of the whole system. And then here comes the heaviest part of the, not yet maybe. The ground, well, maybe this is the heaviest part. You compute the ground state of this Hamiltonian. Now, I mean, this HAB is, if you define this as a matrix, this is chi times D times D times chi. Chi squared times D squared dimensional Hermitian matrix. This is such a matrix. And of course, I mean, it is not the best way to store such a huge matrix as in the form of matrix and apply the diagonalization to that. That's not a very good idea from the technical point of view, but in principle, you can do that. And I mean, more efficient implementation is not the subject of the introductory part of this talk. So, I mean, in any way, in principle, you can diagonalize such a Hamiltonian. And suppose you apply the diagonalization, numerical diagonalization of such a big matrix, then you can, in principle, obtain the ground state of this Hamiltonian. It is CA tilde B tilde, and with some ground state energy. And then the next step is an important step. And once you obtain the ground state for the whole system, A tilde, B tilde, then you form the density operator, which is represented by this diagram. And then you apply the singular value decomposition, or in this particular case, it's just a diagonalization, to obtain two unitary operators, which is represented by U here. And then by using this U, I mean, this U can be used for the renormalization. And because since we added new site, the local dimension of the subsystem becomes much bigger than original dimension of subsystem A, bigger by the factor of D. Because I mean, this is D-dimensional line. So you cannot proceed in this way forever, because every time you do this, you carry out this iteration, the dimension you have to handle, it becomes D times bigger, and you cannot do this forever. So what you have to do is you have to project this chi times d dimensional space back into the chi dimensional space. That's what you have to do. And in order to do that, you have to have some sort of operation. I mean, some sort of projector that project d times chi dimensional space into back into the chi dimensional space. And then in this, by solving this equation, you can obtain such a projector U here. And with using this projector U, you can map this d chi times d dimensional Hamiltonian back into the chi dimensional Hamiltonian. And you can redefine HA as this. And in the same way, you can define the H spin as this. And then by this whole procedure, you updated HA and HA alpha, then you can proceed. You can repeat this procedure until convergence. So this is basically the DMRG. And the important fact here is, in this process, you computed the projector by using the information of this environment here. I mean, for subsystem A, the subsystem B acts as an environment, and by taking into account of such an environment effect, you can define the projector, suitable projector. And this kind of calculation is repeatedly appearing in the all sorts of tensor network calculation. So this is kind of essence, one of the essence of the general tensor network type calculation. And this is how we squeeze the, data, how data compression is done in tensor network type calculation. And that already appears in the DMRG calculation. Okay, and you can apply the same, not really the same, but a similar spirit. You can carry the similar spirit onto the larger dimensional, higher dimensional systems. And probably Van der Straeten may be talking about this because he published a few papers based upon this kind of idea. But anyway, this particular picture was taken from Philip Colbo's paper in 2016. Okay, let me explain what this picture means. Okay, this is a variational principal calculation. And in this case, we consider, at least conceptually, we consider so-called pets. Although we don't directly deal with pets, but at least in the mind, we have this kind of black is better, right? At least in our mind, we have this kind of tensor network. Basically the same lattice structure as the problem itself. So if the problem is two-dimensional, defined on two-dimensional square lattice, we also consider the two-dimensional square lattice-shaped tensor network. But of course, we have this physical index, which is connected to the physical degrees of freedom. So what we have in mind is something like this. And this picture is, okay, if you take a look, if you look at this network from above, then of course what you see is just a square lattice, right? And the meaning of this picture is this is so-called the corner transfer matrix framework. The meaning of that picture is, roughly speaking, this part is represented by this square here, and this part is represented by this small square here. And likewise, this part is represented by this one, right? And in the same way, you decompose the whole infinite lattice into 9 components. And in the central part, we have this green circle here. That's a representation we are using here. And okay, so CA is basically some I don't know. Something like this. However, since we are using this corner transfer matrix representation, infinitely many physical index is represented by, okay, we don't see the physical index here, but we see its physical index here, right? So this part, this central part is actually corresponding to this one. Because this is a, side view. This is side view and this is a top view. And this part in the top view corresponds to this central circle. So anyway, at least formally, the energy is, your variational principle is represented by this equation, where A is the elementary tensor, which is represented by a small circle in the whiteboard picture. So what you want to do is choose such an A that minimizes this energy of the whole system. This H is the energy of the whole system. And because of the variational stationary condition, you can stationary condition can be mapped into the condition of derivative with respect to A. If you take the derivative of this quantity with respect to A, it must be 0. That's the stationary condition. And such a stationary condition is diagrammatically represented by this equation. And this part, blue part, contains the energy, basically. For example, let's come back. Let's look at this picture. This is very complicated, but the meaning of this is not so difficult. This blue part means that it contains at least one piece of H. Please remember that this total Hamiltonian is the summation of the pair Hamiltonians, right? So usually this big Hamiltonian, the whole Hamiltonian, the whole system is just a summation over many pair Hamiltonians. And you just pick up one of these such pair Hamiltonians, right? So depending upon which pair Hamiltonian you choose, we have this, 20 diagrams. If you choose a pair Hamiltonian that belongs to this part of the system, which means that this part of the system, then it corresponds to this diagram. And if the pair Hamiltonian you picked up belongs to this part of the total whole system, then your Hamiltonian, your term, is included in this term. So that's the meaning of this diagram. And then, you can easily verify that if any pair Hamiltonian is included in one of these pictures. So by computing all of these diagrams, correcting all of these diagrams, basically you can compute this H-shaped tensors or environment or whatever you like to call it. And also this type of N, it is often called N tensor, and this is often called H-type tensor, H-shaped tensor. You can as long as you can compute all of these terms, basically you can compute this H tensor and this N tensor, these two things. And once you can obtain this H tensor and N tensor, then the rest is just a eigenvalue problem with respect to this small tensor. That is A. And by solving this eigenvalue problem, you can basically get the optimal solution. And that's the idea. Of course, this is based. In principle, you can do that, but in practice, there are many tips and many technical details you have to worry about. But please don't ask about such a technical details. I don't know that. Well, I know some of them, but actually I have not made a computer program based upon this idea myself, so I don't know. I cannot claim I know every detail of this type of calculation. But at least this is the basic idea. Okay, so this is, I think this is kind of natural extension of DMLG idea to two-dimensional systems. But of course, probably most of you might be more familiar to the so-called TEBD. I don't remember the original name of that, but TEBD. TEBD is probably it is easier basically. The implementation of TEBD is, at least conceptually, it is very easy, and technically also it is. I think it is much easier than this. So probably most of you know my TEBD better than this type of direct variational principal calculation. Basically, TEBD is, multiplying the Hamiltonian many times. Maybe I should have to run this E minus tau BH. And basically, you can apply the imaginary time development evolution operator to the tensor network wave function. And you can repeat this kind of procedure many times, at least numerically. And then the remaining the tensor network state, we can expect that the remaining tensor network state approaches the ground state. That's the same thing as the iteration method for the diagonalization. So yeah, that's easy. Maybe I don't remember right now, but maybe I come back to such a TEBD type of implementation for the optimization of the tensor network later. But this type of calculation is easier and in many cases practical. And actually, we have done several calculations using TEBD type calculation. But if it is possible, this type of calculation gives you better results. More accurate result. Anyway, okay. So, in any way, we are going to see many tensor network state calculations in the coming workshop. Many speakers and many lecturers are going to mention how they apply tensor network state to study the quantum states, various quantum states. And I think this is just one or two example. And but at least I think this gives you already a basic idea to understand their talk. So let's move on to another subject, which is, recent developments, Tensor Network and Neural Network. And yeah, anyway, everybody knows. This was a very big impact. Everybody knows that 3 years ago, AlphaGo defeated the world Go champion Lee Sedol. That was a big thing. And since then, all of a sudden everybody started talking about the artificial intelligence and machine learning, etc., deep learning, etc., etc. And yes, of course, even before AlphaGo appeared, of course, many researchers knew that in principle, artificial intelligence can do all sorts of things, including defeating Go champion, but not many people expected such a thing happen so soon. But anyway, since it happened 3 years ago, then even common people, not really researchers, even outside of the academia, people start to talk about this kind of thing. And now, in order to get any funding, you have to relate your project to artificial intelligence somehow or something like that. So it was a very big impact, AI shock in some sense. So of course, what I'm going to tell you is not motivated by getting more funding. What I'm going to tell you is, purely, from the, curiosity and academic interest, and yeah. So anyway, why not? Using neural network for quantum many-body problems, because after all, what we have been doing under the name of variational principal calculation is kind of machine learning already. We just didn't call variational principal calculation in that way. We didn't call it machine learning, but after all, it's sort of machine learning. So, actually, neural network type calculation is, is not very, extraordinary thing to think about, to imagine. And in fact, on the same year as the AlphaGo appeared, AlphaGo defeated the Go champion, Carlo and Troya proposed the idea. And they were clever, because they started from a very simple network. Not directly jump into the deep learning. What they did was basically the simplest neural network with only one hidden layer, which is called a restricted Boltzmann machine. And basically, they consider this kind of neural network or restricted Boltzmann machine. And the variational wave function, which is represented by this diagram, is formally written in this way. So it has a Boltzmann weight here. And if you take a look, you can easily realize that this is very simple physical system, statistical mechanical system, because this first term represents the magnetic field, external magnetic field applied to the real spins, real variables, or in other words, visible layers. And the second term here, VIHI, is nothing but the external magnetic field applied to the hidden layer. By the way, this small h is not the external field. Small h here is the local variable itself. So HI here is not the external field. BI is the external field applied to the local degrees of freedom HI. And lastly, this last term represents the interaction between hidden layer spins and real spins, visible layer spins, HI and sigma j z. And the whole Hamiltonian consists of these three components, which is very simple and easy to understand. And of course, we have to take the summation over hidden variables, HI. And as a result, you get the coefficient of the wave function, your variational wave function. And basically, they did the Monte Carlo sampling for estimating the energy with respect to this wave function and its gradient with respect to h and w, these parameters. I'm sorry, I was confused myself. This h is not correct. This h should be replaced by a, j, and bi. So in any way, with respect to the variational parameters, then once you can get the gradient with respect to the variational parameters, you can apply the steep descent or conjugate gradient type optimization to this wave function. And as a result, you get the good variational wave function, basically. So, so far so good, but since they were using Monte Carlo sampling, this weight cannot be negative. In other words, as long as you want to calculate the ground state wave function, which has the positive real weight, then this type of calculation might be useful. But if your target wave function, quantum wave function, does not satisfy such a property, then this type of scheme is somehow problematic. You have to think about something else. So actually, they apply this kind of scheme to, I don't remember, maybe square lattice Heisenberg model. I don't remember. Maybe somebody remember, right? And yeah, in such cases, it was okay. But of course, you might want to apply this kind of idea to wider varieties of problems. So you have to think about something else. And here is something else. And this was taken from Carlo, Nomura, Imada's paper last year. And probably Nomura-san and Imada-san will mention at least this work probably. In any way, their idea is just using the variational principle, variational Monte Carlo idea, which I showed several slides back, if you remember. If you remember, I showed, I don't know. Yeah, this kind of idea. I explained already. The important thing is by using this Slater determinant type calculation, you don't have to use Monte Carlo simulation. So the weight can be negative or even complex numbers, if you like, within this calculation. Within this calculation, having negative sign does not cause a problem. So basically what they did is something like that. So they used this type of wave function, and CF is again, okay, this is Slater determinant type wave function, and you multiply goods with a projector and also the projection to some quantum number. which is desirable, and then you can get this Fermion wave function, and you have to compute the projection, overlap between such a Fermion wave function with the spin wave function. Spin wave function is represented by this one, which is analogous to the previous slide. By combining this variational Monte Carlo idea and also the neural network type wave function, combining these two ideas, they came up with some scheme to deal with fermion. Not in this case, not fermion, the spin systems with a negative sign problem. Yeah, that's the relatively recent development. So we are going to hear something from Nomura-san, Nomura-san and Imada-san. Both of these guys will participate in the workshop, maybe third week, maybe next week. You can check yourself the program of this workshop. So, this is quite interesting. And this is another aspect which is related to the neural network type calculation. Okay. Since neural network, deep learning and neural networks, machine learning had a very big impact, which we can even say a shock. There are all sorts of new developments, and this is one aspect. That is the tools. Numerical tools were developed by these companies. So Google created TensorFlow, and Facebook created PyTorch, and these tools help us in making the computer program for related to the tensor network type calculation. Not tensor network, neural network type calculation. But we can actually use at least use the idea, the similar idea for tensor network calculation. But in some cases, we can directly use these libraries itself in the tensor network calculation. But anyway, the point is, if you have some experience in neural network type calculation, probably you know that the backpropagation is the main part of the neural network calculation. Or maybe input and output is also a heavy part, but anyway, backpropagation is a core part, and it is tedious in neural network coding. In particular, if you want to try many different types of network structures, then you don't want to make your program from scratch. Every time you change the structure of the network. So what you want to do is that you just design the network structure, and then the rest of the work can be done with, by the libraries or other software. That might be good programming stack. And these tools, these libraries help us in that way. So if backpropagation and all sorts of differentiation part can be taken care of by some software, the user only needs to design the network structure, which is often called the data flow graph. I think the data flow graph is a terminology of TensorFlow, maybe really not general terminology, I don't know, but sometimes called the data flow graph. And then the essential idea is actually the so-called automatic differentiation. And basically automatic differentiation does this job. Automatic implementation of backpropagation. And such an idea is supported by these libraries. And what is automatic differentiation? Automatic differentiation is basically just a chain rule. automatic differentiation is just a chain rule. Anyway, I mean, our calculation, tensor network calculation included, is almost always of this form. I mean, you start from some input, maybe some elementary tensor t, and then you apply some transformation, some arithmetic transformation, and then you repeat many different types of arithmetic transformation many times, and in the end you obtain the answer. In the case of tensor network calculation, the answer might be the expectation value of the energy. And suppose every arithmetic transformation is differentiable, then you can apply the chain rule, basically. I mean, this is a differential operator with respect to the k minus 1's variable, and such a differential operator can be defined as a some matrix times differential operator with respect to xk. So, I mean, this is chain rule, basically, right? So there's nothing new here. It is, I mean, very easy. So this, as I said, this is just a chain rule, but typically very tedious to program, because, I mean, if I drew this dependency of variables in this way, I mean, it may look straightforward, but I mean, in practice, I mean, the dependency among the various variables is kind of form trees or networks, and for such given network, I mean, you apply this chain rule depending upon such a complicated dependency among variables. Such a thing, it can be tedious, very tedious. So the idea of automatic differentiation is I mean, systematically do this kind of thing without the hand coding. So basically, okay. Then this automatic differentiation idea was explored by these guys, Haijun Liao, Lei Wan, and Tao Shan. All of these guys will appear at some point of time in this workshop. So I think we can expect that we can learn about automatic differentiation used in tensor network calculation from them. And this is very interesting development. So in any way, let me just briefly mention what they did. This is actually the corner transfer matrix type calculation of energy. And this is I already erased the diagram, but if you remember, I mean, corner transfer matrix, you still remember, right? And in the central part, we have pair Hamiltonian. This is pair Hamiltonian, and this whole diagram is this. Okay, this part is just a partition function, and not partition function. This part is the normalization of okay. This part is basically that diagram represents basically these C, and this one is since we have pair Hamiltonian sandwiched in this part. This is pair Hamiltonian Hij. So this part is basically CH12C. So basically, the whole thing represents the expectation value of the pair Hamiltonian. And they actually computed this quantity by using, not just computing this quantity, but also the differentiated. They differentiated this quantity with respect to, each, building block tensor by using the an automatic differentiation idea. And as a result, they, of course, since they can compute the gradient with respect to the parameters, they can apply the steepest descent type calculation optimization. So this is the result, and this blue line corresponds to the result of automatic differentiation with, this, a conjugate gradient type optimization, I believe. And these are the results from the, this is simple update. This line corresponds to the so-called simple update, which is one of the method implementation of the TEPD idea. And this is full update. This yellow line is full update, and it is also one of the implementation of TEPD method. But it is believed to be better than a simple update. So actually, it is better than simple update. And Colbo's data, I think it is the variational calculation, right? So, I showed many diagrams, 20 diagrams before, if you remember. And this red line is Colbo's calculation by using the variational optimization. So it is, actually, now you see that that kind of idea gives better results than the TEPD type optimization. So, and then their result is quite competitive, as you see here. So, this is also interesting development. And here is a little bit of the technical part of this type of calculation. And of course, as I said, basic idea is just a chain rule. You apply this chain rule many times in a systematic way. But of course, you might be curious. What happens for a more complicated operation like diagonalization? So suppose this type of calculation, this diagonalization operation appears many times in tensor network type calculation. In the form of singular value decomposition. But singular value decomposition is basically similar, very, the same as the diagonalization. So, let's think about diagonalization. How can we apply the, chain rule for such a complicated operation? And this is a result. And this is the, actually x bar is actually the differential operation with respect to x. And the u bar is differential operation with respect to the, elements of this unitary matrix. And d bar is the differential operation with respect to the diagonal, elements, eigenvalues. So, I don't want to derive this equation right now, but we just take it for granted. And differential operation with respect to original matrix X can be expressed in terms of differential operation with respect to U and D in this way. And here it appears Fij, which is inverse of difference between j's eigenvalue and ith eigenvalue. And this circle represents Adama product, which is an element-wise product of two things. And as you can easily imagine, once you get something like this, what would happen if there is a degeneracy? Right? So this kind of operation becomes singular when there is a degeneracy. And also, we don't use this whole thing. I mean, what we often do in the tensor network type calculation is truncation. As we have already seen the truncation in the DMRG, right? Even in DMRG, we have to truncate the eigenvalues. So truncation means that first we sort the eigenvalues in the descending order, and we cut at some point. And such a procedure, can we differentiate such a procedure? That's the question. So how about degeneracy? That's one question. And is truncation of D differentiable? I mean, these, of course, you become curious about these points. Although basic idea is that just chain rule, but still, I mean, if you start thinking about the technical details, you quickly notice such a difficulty exists. And please ask them. I don't give the answer here. I don't want to spoil their talk. Okay. So third topic. I have only 30 minutes left, so maybe I should be much quicker than this, because I think I have up to 7. Anyway, okay, so far we have already seen tensor networks. Already we have some idea what it is. But I think now it is good to, review at least the most basic properties of tensor network states. Now, first of all, I would like to mention that most classical models defined on lattices, most classical models of classical statistical mechanics are already a tensor network itself without doing anything. For example, if you think of the Ising model, for example, this is just Ising model, and however, you can view this Ising model as tensor network in the following way. If you, usually whenever we draw the picture of Ising model, we represent each spin as a dot or circle or some point-like object. But instead of using point-like object, we can also represent each spin as a line, right? So this is Ising spin, S4. This is Ising spin, S3. This is Ising spin, S1. And then by this square, maybe you can represent the Boltzmann weight related to these 4 spins. Let's say, for example, the interaction between S1 and S2 is included in this here, and S2 and S3 is included here. So this TP, this tensor, represent the interaction among these 4 spins. And this is obviously, this number obviously depends only on S1, S3, S3, S4. So you can regard this object as a rank 4 tensor. So in this way, you can regard almost every discrete statistical mechanical model as a tensor network. So it means that all the construction techniques we develop for quantum systems can be also used for studying the classical statistical mechanical models, and vice versa, of course. And if you think of any good way for taking the construction of tensor network representing the classical statistical model, then we can use the same technique for studying the classical quantum systems as well. That's the first remark I would like to make. And this is PEPs we have already encountered many times. So as I said, the PEPs is basically the same shape of the network, which has the same shape as the program itself. But we have, physical legs. And of course, tensor network calculation, as we have already seen, in the tensor network calculation, we have two procedures. We have to think about two procedures. In the case of classical system, classical statistical mechanical model, I mean, we know what each tensor is. For example, in the case of the Ising model, we know what this tensor is from the beginning. However, if you want to apply the tensor network state idea for studying the quantum systems, then at the beginning, you don't know what each tensor is. So the first step for a quantum application is to obtain each tensor by some method. And for that purpose, we sometimes use the TEBD, or in some cases, we use the variational principal calculation, as I explained already. So there are several methods for optimizing the tensor. In other words, obtaining this tensor. And then after obtaining this tensor is not the end of the story. You have to take the summation. You have to take the contraction of this network. And in this contraction process, you can use, as I said, you can use exactly the same technique as can be used for classical systems. And for that, typical example is corner transfer matrix method, which I already explained a little bit. That's one good way to do, but there are many other ways to compute the contraction. Okay, why should we consider this type of network? There is some reason, so-called area law. Maybe most of you already know this, but anyway, since this is an important aspect, let me repeat it anyway. Okay, let's consider the entanglement of typical state. There is actually the theorem that if you consider the entanglement entropy of subsystem A embedded in the whole system, which is represented by omega, then if you take a quantum state at random, quantum state for the whole system at random, which in other words, in more formal language, if you take this entanglement entropy with respect to the invariant Haar measure, which basically means that you choose any quantum state for omega at random, then it is of this order, meaning M is the dimension of Hilbert space of subsystem A. And of course, such a dimension of Hilbert space of subsystem A is proportional to the volume of subsystem A. So if you pick up the random quantum state for the whole system, then the entanglement entropy of subsystem A is proportional to the volume of A. That's the theorem. So for a randomly picked up quantum state, entanglement entropy is proportional to the volume. So this is a typical case, in some sense. In some sense, typical case. However, what we are interested in, the condensed matter physics, is not typical. For example, for one two-dimensional or higher free boson or fermion with finite gap satisfies this rule. That is, the entanglement entropy is bounded by the area or boundary, volume of the boundary, volume of the system. It's not the volume of the system, it's the volume of the boundary around A. Therefore, it is proportional to L to D minus 1, not to L to D. So, typical case satisfies area law rather than volume law. So, in this sense, finite dimensional quantum state which we are usually interested in are very special. It's not typical. So the idea of tensor network or idea of TEPS is basically making maximum use of this part. I mean, if our system is, if we are interested in the, generic quantum state, then tensor network state may be not so useful. But since we are interested in this special state which satisfies the area law, we might get something better out of TEPS type wave function, because TEPS type wave function automatically satisfies the area law, because the TEPS type wave function is represented by this diagram, right? And if we want to compute the entanglement entropy of this subsystem, it means that the kind of correlation between this subsystem and the environment. So as you can easily imagine, it is bounded by the number of connections connecting inside and outside. So actually, it can be rigorously proven that the entanglement entropy between inside and outside is bounded by twice as much of the number of bonds on the boundary times log d, whereas log d is a dimension of each bond, which is order 1. Therefore, TEPS satisfies the area law. And this is the reason why using TEPS you can get something, you can get a better result. Okay, the fourth topic is tensor network states as prototype of new quantum states. So far I have been talking about how you can use a tensor network state as a variational wave function. But instead of using it as a variational wave function, maybe we can use it, or maybe we can study it as a prototype of new category of states. And such an example already we are familiar with. That is AKLT state. AKLT state is very well known because it is believed to be the same category as the Haldane state, which is the ground state of spin 1 chain, antiferromagnetic chain. But it is hard to obtain the exact ground state of the spin 1 antiferromagnetic chain, but it is, on the other hand, it is very easy to represent the AKLT state, which is physically, many people believe that physically, AKLT state and the ground state of ground state of the S1 antiferromagnetic Heisenberg model, these two things are essentially the same, share many properties in common. So AKLT state, instead of Haldane state itself, it is much easier to deal with AKLT state. And AKLT state can be represented by the matrix product state with just bond dimension 2. This bond dimension is 2. And this representation is not approximate. It's exact representation. And you basically you consider that this tensor T, which has physical bond dimension 3. Of course, we are talking about spin 1 system, so this bond has a dimension 3, but this bond has a dimension only 2, and yeah, basically this is it. So we know that AKLT state is already one such example. Instead of working with ground state of Heisenberg model, maybe we can work with AKLT state, and since it is much easy to see and much easier to study because it has a very simple matrix product or tensor network representation. So this is one example.
And here's another example, which might be maybe more interesting. That is stack model or toric code model proposed by stack. And toric, probably most of you know that the toric code is one of the simplest solvable models. And this model is discussed very heavily in the context of the quantum information, topological phase, and Mayonnaise, fermion, and etc., etc. And the model is defined very easily. You consider square lattice, and then here again we define spin on the edge, not on the point, not on the lattice point. Spins are living on the edge. And for Z, for this part, you multiply Z components. Here, Z component of this spin, Z component of this spin, Z components of these four spins, taking the product of these four components, then that's the definition of this capital ZT. And likewise, you can define capital XP as a product of X components of these four spins. And then by this expression, you take the summation over all capital X on this side, on this kind of configuration, and also you take the summation over all Z, capital Z operator for all the brackets. Then you get the Hamiltonian for the toric code model. And actually, I prefer to use this graphical representation. In this representation, spins are defined on corners again. Here spins are living on the corners. And for X bracket, you define this. For Z bracket, you define this. And then take the summation of all such operators gives you Hamiltonian toric code. So this is toric code model. And the ground state. What is the ground state of toric code model? And it is easy to see that the toric code model's ground state can be represented as, again, as a very simple tensor network state. Basically, something like this. So this is the ground state of the toric code model, and this is the basis function, basis state. Right, this is the projector, and this is the one. And if your wave function can be represented by such an equation, you can easily see that such an equation, such as states, can be also represented by the tensor network, like this. Here the tensor is defined in this way. At each corner, tensor Ti is defined, and in this case, again, the virtual points is two-dimensional. But there are four virtual points: alpha, beta, alpha prime, beta prime. All of these things take two values. It's binary variables taking +1 or -1. And this sigma I is a physical index, physical bond. So it also takes +1 or -1. And by definition, this Ti, the element of Ti is non-zero only if alpha equals beta. This index and this index are the same. Same +1 or same -1. Only two possibilities. And the same thing applies to alpha prime and beta prime. Alpha prime must be the same as beta prime, otherwise this tensor gives you 0. And then finally, this physical index must be a product of tau I, alpha, and alpha prime. So this, so this is the condition. This is the definition of T. I. So in this way, you can represent the toric code ground state as a simple tensor network state. So, I mean, this was known. I mean, I forgot to write down the reference. I mean, this is not our finding. I mean, this was known for some time. And quite recently, toric code state is some special case of honeycomb lattice Streiff ground state, right? I mean, there is another version of Streiff model on the honeycomb lattice. And the Streiff model of honeycomb lattice has a either gapless ground state, so-called Streiff spin liquid, gapless Streiff spin liquid, and in some cases, the same model gives you the toric code type ground state. There are two cases. And so far, until quite recently, I believe that there was no simple tensor network representation of the gapless Streiff spin liquid. And quite recently, anyway, let me briefly explain what is the problem. So this is another version of Streiff model defined on quantum lattice. And depending upon the direction of this bond, let's suppose, this is z direction. Let's define this vertical direction is z direction, and this is x direction, and this is y direction by definition. And for z direction, we consider S sigma z coupling. And for x direction, we consider sigma x interaction, and likewise for y direction, we consider sigma y interaction. That's the definition of the Streiff honeycomb model. And in the limit of strong z coupling compared to y coupling and x coupling, if the z coupling is much stronger than the other y or x couplings, then this model is basically equivalent to the Streiff model. Toric code model. However, if these three types of couplings, Jx, Jy, Jz, all of these couplings are more or less equal, or exactly equal, let's say, then the ground state is gapless. That is known. Because there is there is an exact solution to this model. So, however, the exact solution is usually described by the Majorana fermions, and this fact makes its physical picture hard to comprehend because, Majorana fermion is hard to observe. So, so recently, we considered some state, which we call a loop gas state. And this loop gas state plays a similar role as the AKLT state. AKLT state is not the ground state of the Heisenberg model itself, right? There is a difference. But many people believe that essentially the physical property of AKLT state is the same as the physical property of the Heisenberg model ground state. So, in the same sense, we propose the loop gas state as an analog of AKLT state for the ground state of the Heisenberg chain. The meaning is the following. Okay. Loop gas state is defined. Okay, first let's define loop gas state first. Loop gas state is this 111 state, whatever it may be, with this projection operator QG. And G depends on this operator. This operator depends on graph G, and graph G is loop configuration. And the summation is over all possible loop configurations. And actually, this initial state, 111, is the fully polarized state in 111 direction. And then you apply this operation which we call the loop gas projector. And loop gas projector is something like this. So for example, if there's, it consists, this G is graph, and G consists of loops. In this case, 2 loops. In this case, another 200 loops. And there are so very, very huge number of possible graph configurations, loop configurations. And this summation is over all such graph configurations. And then, by definition, we define the loop gas state as this. Oh, by the way, I have not explained the definition of QG. The definition is not so difficult. For example, along this line, along the loop, you multiply either Sx or Sy, Sz or Sx. Power spin, sigma Z or sigma Y or sigma X. The rule is rather simple. Details, Hyunyoung Lee is going to talk about the details of this development, but anyway, let me briefly mention. If we have this type of loop, then this is equivalent to sigma Z, sigma X, sigma Y, sigma Z, sigma X, sigma. This is nothing but flux operator, so-called. But this is kind of extension of flux operator. So now the definition is more or less clear, right? So by defining this kind of state as a loop gas state, then you can show that loop gas state, the overlap between 2 loop gas states is exactly the same as the partition function of the classical loop gas model exactly at the critical point. And this loop gas model is, maybe some of you are not so familiar with loop gas model, but it is basically the same, equivalent, mathematically dual to triangular Ising model. Suppose you consider triangular Ising model, and if you are familiar with the low temperature expansion, if you apply the low temperature expansion to the loop gas triangular Ising model, then the result is the loop gas model. And here, loop corresponds to the boundary of the cluster in the triangular Ising model. That's the correspondence between triangular Ising model and the loop gas model. So there is one-to-one correspondence, exact correspondence, and triangular Ising model at exactly TC is mapped to the loop gas model with velocity of 1/3, which is also exactly at critical point, and that's the loop gas state. So you can show that all the correlation function of loop gas state is the same as the correlation function of the classical loop gas model. And however, this is just loop gas model. And what's the connection between loop gas state and the Kitaev model? That's the question.
So the triangular Ising model is a ferromagnet.
Yes, right. This is a connection. We can have several sequences of answers starting from the loop gas state. So loop gas state is the zero sum. Let's say it's a zero answers, and we can construct. We showed quite recently. We showed that there is a series of answers which starts from the loop gas state and all the way down to the Kitaev Heisenberg model ground state in this way. And okay, for loop gas state, we don't have any variational parameter. And for the first answers, I'm not going to explain the details of this wave function, but let me just say that this new wave function is just one variation parameter, and this second wave function, second ansatz, have two variational parameters. Only one or two variational parameters, you can make the energy extremely close to the correct exact ground state. And in principle, you can go on in this way. And but already in the second ansatz, the ground state energy is 0.007%. Only the difference is 0.007%. So, from this result, we believe that this is the, continuously, connecting to the Heisenberg model ground state. But please ask Hyun-Yon for the details, every detail. Okay. Yes. Maybe I'm going to skip some of the things, but which part I should skip, I wonder. But anyway, Tensor Network is very important. Tensor Network-based real space renormalization group is very important. And actually, maybe that's the most important application of Tensor Network, because if it is only for the variational ansatz for some given quantum state, then neural network ansatz may be quite as good. So, but when it comes to the exact renormalization group method, which I'm going to tell you a little bit, maybe the Tensor Network state is the only choice, maybe. Anyway, Tensor Network renormalization group, the simplest one is going like this. Starting from square lattice, then you apply the singular decomposition to each tensor, like this. And then, as a result, you get some picture like this. And then, taking the partial contraction for each small squares, you get some new tensor as a result of partial contraction. And then, you get renormalized tensor network. So this is a real space renormalization group. But of course, in order to make the whole procedure exact, this line must be twice as thick as this line, because this line must carry the same amount of information of these two lines. So in order not to make any approximation, this line must be twice as thick. So as a result, this line must be twice as thick. However, again, such a procedure cannot go on forever, because every time you apply this procedure, the thickness of the line is multiplied, and it's doubled. It's impossible. So somehow you have to truncate. You have to introduce some truncation in this procedure. Again, that's another data compression in condensed matter physics. Anyway, by this type of, as I said, we have to introduce some sort of truncation, and there is a theory that is very important, kind of central theorem in tensor network approximation, that is low-rank approximation. The Eckert-Yang-Mansky theorem says that we can obtain the best low-rank approximation by truncating the small singular values. That's a very simple theorem, right? So in other words, suppose we can singularly decompose of the matrix A like this. Then this the best low-rank approximation to this matrix A can be obtained by replacing this lambda by this truncated matrix. That's the theorem. And everything else, more or less everything else follows from this theorem. And then, this Roland approximation appears everywhere in tensor network calculation. For example, in the case of so-called high-order tensor network renormalization group, what we do, essential approximation is something like this. Essential approximation is, original form is this, and we introduce some truncation or some projector in this form, and we want to make the difference between the original one and the approximation as small as possible. This is basically error, the approximation. And as long as this line is smaller than the twice of these two lines, then it is a Roland approximation. And however, this problem is not exactly the same form as the original Roland approximation appeared in the Eckert-Young-Marsky theorem, but it is kind of application. You can also find a solution based on the previous theorem, and the result is shown in this way, but I don't think I have sufficient time to explain all the details of this solution. But the solution, as far as I know, maybe this solution was already known for some time, but as far as I know, this paper is the first paper I saw the solution. Yeah, wasn't do you know the original paper for the solution? But anyway. There is a solution. That's the most important thing. And once you obtain this kind of solution, then you insert this kind of projection operator everywhere. In this way, for example. Then by defining this part as a single tensor, by partial contraction of this part, then you get some new tensor here. And the thickness of this line is again the same as the original the thickness of this line. So you can repeat this procedure many times. That's basically the HOTRG. Okay, I think time's up. Well, there are so many other things, interesting things, or important things, but no, I don't think I have time for these. Tensor network for machine learning. Yes, yeah, this is also okay. Yeah, let me just flash every thing. So here is the improvement of TRG, and the improvement comes for the redundant entanglement loop, and there is a very clever way of removing this redundancy. This redundancy kills, eats up the capacity of tensor network. So we definitely want to remove this type of redundant entanglement loop. And this is a very clever idea. And I think Harada-san contributed some good idea to this problem, but I'm not sure whether Harada-san is going to talk about this thing during the workshop. Maybe not. Okay. And tensor network for machine learning. Recently, Standen-Meyer and Schreck and other, there are many other papers of now, but I think this was the first one, at least among the first ones. They use the matrix product state for pattern recognition. This is a famous benchmark problem. Everybody can download the program, and this is the sample. And they use they constructed a framework of the machine learning based on the matrix product state. And basically, LPS and the DMRG-like optimization can be used for pattern recognition. That's what they showed. And also, Tensor Network, there is some attempt to use Tensor Network representation for the pattern recognition or pattern storing. And in this particular example, they store these images in the form of a ring of 4 tensors, and they observed performance improvement by using this kind of ring structure compared to the just chain structure. So here is some attempts for the pattern recognition by Tensor Network. And yes, here is the entanglement loop problem, which I have mentioned already. This type of redundancy is always there. But yeah, this is a very technical problem, but I think this is one of the most important technical problems related to the tensor network calculation. Okay, this is how we are trying to solve this problem, but Kyung-Yong and me tried something, and the result so far seems to be promising, and this is the error, and this is the temperature, and this is actually a two-dimensionalizing model, and this is the conventional old method, and this is the method we propose that asking. And here is some applications I would like to mention. And the first one, of course, frustrated spin system is one of the most important targets of this type of tensor network approaches. And here, the Okubo-san used tensor network calculation for the magnetization process. This is a magnetization, and this is a magnetic field for the Kagome lattice compound. And they clarify the characterization of magnetic plateaus. That's what's going on this part of the magnetization processes. And they clarify the effect of Jaroszynski-Moriya interaction. And also, maybe Harada-san is talking about this, right? And he recently developed a scheme for studying the dynamical system with the tensor network representation. In this particular example, he computed the Renyi entropy at the critical point as a function of time. And this is the logarithm of time, and this is the Renyi entropy. And Renyi entropy, by the way, is a difficult quantity to measure by other methods, for example, Monte Carlo simulation. And he successfully obtained the value of z, dynamical critical exponent. And also, yes, Inokun sitting over there, taking care of the camera. He recently came up with a very nice framework for studying the boundary surface physics with respect to the tensor network renormalization group calculation. This is surface magnetization, it's a scaling dimension. Nice. And also there's other possibilities for applying the tensor network type calculation for other kinds of methods. That is the QCD, lattice QCD. We are going to hear the developments in this direction in the first symposium, meaning next Monday. Kawashima from Tsukuba University is going to talk about present status of this kind of trial attempts. Of course, this lattice higher density QCD phase diagram, completion of it is very, very, very difficult. But towards that, he developed many interesting things. We are going to hear that. Okay, this is a summary. I have talked many things, but still there are many other interesting topics, and please enjoy them. Thank you very much.